Everyone, and welcome back to The Explainer. Today we are taking a fascinating, entirely objective dive into the complex science and safety of a chemical you have absolutely heard about in the news, Bisphenol A, or BPA. We're going to treat this as a true scientific investigation. We'll be crunching the data, unpacking the chemistry, and looking super closely at the methodologies used by both regulators and independent researchers to figure out exactly what's going on with our food packaging. So let's jump right in.
Here's our quick game plan for today. We are going to meet bisphenol A, trace how we're exposed to it, measure the actual risks, unpack the whole low-dose debate, and finally, look at the official regulatory verdict.
Okay, let's kick things off with Section 1, Meet Bisphenol A.
So what is it really? At its core, BPA is a chemical monomer. It is basically a building block. It's primarily used to produce two things you've probably got sitting in your kitchen right now. First up, polycarbonate plastics. These are those hard, clear plastics you often see used for feeding bottles or food storage containers. And second, it's used to make epoxy resins. These resins act like a protective lacquer on the inside of metal food and beverage cans, and they're there to stop the metal from corroding into your food.
To really understand what we're talking about here on a molecular level, take a look at this chemical structure. This is 2,2-bis-4-hydroxyphenylpropane. I know it's a mouthful, but that is the formal scientific name for what we all just call BPA. It is produced by the condensation reaction of phenol with acetone. And grounding ourselves in this hard science is absolutely crucial, because it is the specific shape and behavior of this very molecule that sits at the center of the massive global safety debate we're about to explore.
Moving right along to Section 2, let's trace our everyday exposure and see how BPA actually enters the diet.
BPA gets into our food through a process called migration. Basically, microscopic amounts of the chemical transfer from the packaging into whatever food or liquid is inside. Now, it's really important to note from the source data that if the epoxy resin inside a can is properly cured during manufacturing, the residual amount of BPA is actually remarkably low. Tests on polycarbonate bottles also generally show very little migration. But, and this is a big but, research from 1998 noted a very specific exception. They found elevated migration, around 3.9 micrograms per kilogram, in a brand new, unwashed bottle. This tells us that degradation, or even just skipping that initial wash, can definitely play a role in how much of the chemical leaches out.
Let's put some real numbers to this. Check out this table breaking down dietary exposure across different age groups using conservative estimates from the European Food Safety Authority. The contrast here is kind of wild. A 3-month-old infant consuming only breast milk has an estimated exposure of just 0.2 micrograms per kilogram of body weight per day. But look right below that. A 3-month-old fed formula from a polycarbonate bottle jumps all the way to 11 micrograms. And a 6-month-old using a polycarbonate bottle and eating commercial foods, they sit at the highest estimate of 13 micrograms. Meanwhile, an adult consuming a whopping 3 kilograms of commercial food daily is only exposed to about 1.5 micrograms. So it's incredibly clear that infants fed from polycarbonate bottles represent our highest exposure demographic.
That brings us to Section 3. We have our exposure numbers, so now let's measure the actual risk by comparing those to the official limits.
I really want you to focus on this massive number right here. In toxicology, scientists look for something called the No Observed Adverse Effect Level, or NOAEL, in animal studies. It's exactly what it sounds like, the highest dose at which absolutely no harmful effects are seen. Well, the US FDA estimated the maximum potential exposure for adults to be about 11 micrograms per person per day. The NOAEL from animal studies is roughly 300,000 times higher than that daily human intake. We're talking about a buffer of hundreds of thousands of magnitudes between what we ingest and what causes observable harm in standard laboratory tests.
On top of that, regulatory bodies establish a tolerable daily intake, or TDI. This is a highly conservative threshold engineered to protect human health over an entire lifetime. Even when using the absolute highest, most conservative exposure estimates we looked at earlier, like that 13 micrograms for a 6-month-old infant, the total exposure remains less than 30% of this established safety limit across all population groups. So based purely on conventional risk assessment math, our exposure sits very safely in the green zone.
Which leads us to Section 4. If the math is so reassuring, why the controversy? Let's weigh the scientific conflict in the low-dose debate.
There are essentially two warring factions in BPA research. On one side, you have the conventional studies. These are your gold standard tests required by regulators. They test very high doses to definitively find where toxicity begins, establishing that NOAEL we just talked about. In these tests, no reproductive or developmental effects were seen, except at massively high doses, like 50 milligrams per kilogram.
On the other side, though, we have non-conventional studies. These independent researchers argue that BPA, which is known to have weak estrogenic activity, shouldn't be tested like a traditional poison, but rather like a hormone. So they test very low doses, doses way below the regulatory limits, and their findings suggest it disrupts the endocrine system. The crucial sticking point here? Regulators argue these non-conventional studies suffer from a serious lack of strict reproducibility.
Let's look exactly at what the non-conventional side is reporting, because it's fascinating. Out of 115 in vivo studies on low-dose effects published up to 2004, 94 of them actually reported significant effects. We're talking about observations like increased postnatal growth, the early onset of sexual maturation in females, increased prostate size in male offspring, altered immune functions, and even neurotoxic and behavioral effects. The working hypothesis here is that even at tiny, everyday doses, BPA can mimic estrogen in the body and trigger these developmental changes.
But remember, as an objective explainer, we have to look at the full picture. Why haven't regulatory agencies rewritten the rulebook based on those 94 studies? Well, the EFSA and other agencies present a very specific counterargument. First, they state that these low-dose effects in rodents just haven't been demonstrated in the robust, reproducible way required for official risk assessment. But the second point is arguably the game-changer, toxicokinetics. The way a rat's body processes BPA is fundamentally different from a human's. In humans, clearance from the blood is extremely rapid. We efficiently metabolize BPA in our liver into hormonally inactive conjugates. Because of this, regulators argue you literally cannot just map low-dose observations from rodents directly onto human health.
All right, let's bring it all home in Section 5, the regulatory verdict.
Let's walk through this timeline to see how the guidelines evolved as the science got better. Back in 1988, the US EPA set an initial reference dose. Fast forward to 2002, the European Scientific Committee for Food reviewed the data, but they felt there was enough uncertainty that they set a temporary tolerable daily intake with a massive safety buffer, an uncertainty factor of 500. But by 2007, things shifted. The EFSA reviewed an extensively strengthened database on repeated dose toxicity, reproduction, and crucial new data comparing primate and rodent toxicokinetics. Because of this robust new evidence proving that humans actually clear the chemical quite quickly, they removed previous uncertainty factors, dropping the safety factor from 500 down to 100 and established a full TDI of 0.05 milligrams per kilogram of body weight per day.
So, after all that research, what's the bottom line? Based on comprehensive risk assessments, the established tolerable daily intake, and the human body's proven ability to rapidly metabolize the chemical, the consensus from both the US FDA and European regulatory bodies is remarkably clear. I'll just read it. There's no current health risk to consumers from using packaging containing BPA at current exposure levels.
But you know, science is never truly settled, is it? It's a constant, ongoing process of discovery. Agencies like the FDA have explicitly stated they will continue to evaluate new research as it comes in. And that leaves us with a pretty fascinating final thought. As analytical methods become even more advanced and our understanding of the complex human endocrine system deepens, how might future toxicological research shift this ongoing scientific consensus? It is a great reminder that while the current verdict is clear, the scientific investigation into our everyday environment never really ends. Thanks so much for joining me on this explainer, and keep questioning the science around you.